Hopefully today we may be able to finish with the reviews. I hope so that we can continue. But then we have already introduced the Cartesian vectors, I suppose, isn't it? But those ones were in 2D, okay? So here we'll express the forces in Cartesian vectors in 3D, which is just addition of another term for the z-axis. And then we'll determine the magnitude and direction of a Cartesian vector in 3D. We did the same thing for 2D, and then carry out some addition and subtraction of Cartesian vectors. So first of all, to define the 3D coordinate system, we use what is called the right-handed coordinate system, which is this: the thumb of the right hand points in the direction of the positive z-axis when the right hand fingers are called about this axis and directed from the positive x-axis towards the positive y-axis. Okay, so they point toward the positive y-axis and directed along the positive x-axis. So we'll be using this as our reference coordinate system. Y, X, Z, okay, unless otherwise stated. So this is the right-handed coordinate system which we'll be sticking to, and don't forget all the axes are orthogonal, okay, meaning they are at 90 degrees. And by this, to visualize this practically or in 3D system, it means XY constitute a plane upon which the z-axis is perpendicular to that plane. If you take this table as a plane, let's say standing from here, let's assume this is the y-axis, this is the x-axis, and then z-axis will be pointing upwards. Okay, so this is a plane. It constitutes a plane upon which the z-axis is vertical, is perpendicular to that plane. The plane is consisting of the x and y axis. Okay? Now the rectangular components of a vector, just similar to what we did for the components of 2D, which if we have x, y axis, you have a force in 2D. It has component, isn't it, fx and fy, right, along the axis. The same thing here. If you have a vector A, it has component along z, az, ay, and ax. Okay, so how do we find the resultant? The resultant is A, and how do we evaluate it? Very simple, right? You can consider, because here you can consider this plane, the horizontal plane, ay and ax, isn't it? And you can find a resultant, A prime, which is given by what? Ax plus ay in vector form, isn't it? Yes. In Cartesian vector form. And then you now consider A prime with the az, isn't it? Which will be given by A. So A will be equal to az plus A prime, isn't it? And when we substitute A prime as ax plus ay, A is equal to ax plus ay plus az, which is just the same thing we are saying here, that the vector is given by the sum of its components along the axis. Simple, isn't it? F is equal to fy plus fx. But here is in 2D, they should all be in vector form, isn't it? Fx plus fy. The scale or the breakdown of this, the horizontal component is the scalar, isn't it? And I, isn't it? And then for the y component, we have fy and j. This fy, depending on what is used to determine the direction of the vector, can be given by f sine theta, right? Depending on the angle of inclination, if it is to the horizontal, right? And this one is f cos theta, isn't it? If the angle of inclination is to the vertical, you interchange. This becomes cos alpha, and this becomes sine alpha. Or if you want to use the slope triangle, you can use the similar triangle also and adjust the direction, isn't it? So the same thing here, the vector in 3D is the sum of all the components along the three Cartesian axes. We mentioned Cartesian unit vector before, right? Where we said it defines the direction of the coordinate axis. For y, we have j. For x, we have I. And for z, we have k. All these are unit vectors defining the directed along the coordinate axis and defining their directions. Okay? Which is the same reason why here we have fx, I. Magnitude and direction, magnitude and direction. Now we want to give the general definition of what a unit vector is, because unit vector is not just to give the direction of the coordinate axis. Okay? That is just a special case, which we call them Cartesian unit vectors. We have a unit vector which serves the purpose of defining the direction of any vector. Okay? And that is defined a unit vector is used to specify the direction of a vector. The unit vector has a magnitude of 1 and it is a dimensionless vector. If you have a vector A, you have a unit vector in the direction of that vector whose magnitude is 1, and mathematically is obtained by dividing the vector in Cartesian form over its magnitude. Okay, this is bold and this is, normal. I mean, unbolded font. So this is the vector over its magnitude, and you must indicate the subscript to indicate the vector that the unit vector is giving the direction to. Okay, UA means this unit vector in the direction of vector A. Okay, and is given by vector in Cartesian form over its magnitude. Okay. Now, if you remember previously, what we'll be doing in the next couple of hours is we will try to find some other means of deriving or generating the Cartesian vector form. Okay, we have started that before in the 2D, where we used the rectangular coordinate system and the components of vectors along the x and y axis, where when we have vector f, we have fxi plus fyj, isn't it? That defines the vector in Cartesian vector form, and that is one of the ways. Okay, we have other ways that we are going to consider. Okay, which is the second one is using the unit vector. We can use the unit vector to now get the Cartesian form of the vector, isn't it? Because once we know the unit vector and we know the magnitude of the vector, then we can get the Cartesian vector form, isn't it? So let's see. Yeah, this we explain, ijk directed along the axis, and then the representation just the same way as we did for 2D. For the x-axis, we have aix, axi, ayj, and azk. Okay, and the vector is now given by the sum of its components. So here we are just adding this last term, isn't it? Because in our previous class we considered 2D case. And then to express the unit vector using the definition here, because this A is given by this, okay? So if we substitute A as this, we have this one, okay? AX over A, I plus AY over A. All these are scalar components, isn't it? They are all scalar components. Now, magnitude of a Cartesian vector, just the same way we did before. We just square the coefficients of I, J, and K, as we did for the 2D case. Okay, to get the magnitude, we square the coefficients. Okay, square root of AX square plus AY square plus AZ square. Now, direction of a Cartesian vector. Here, the direction is slightly different from the 2D case. In 2D, we only have one angle, isn't it? Because it's either along the x or along the y, isn't it? Simple, straightforward, and direct. But for this one, you have angle of inclination to each of the axes. You have alpha inclined to the x-axis, beta to the y-axis, and gamma to the z-axis. Okay? And these are called coordinate direction angles. And they define the direction of the vector completely. Okay? If you look at this, cos alpha, if you take cos alpha, if we want to find alpha, this is alpha, right? Can you see that? So this becomes 90 degrees, right? And then when you take cos alpha, it will be ax over a, which is the hypotenuse. I hope you can figure out the box very well in 3D. Okay? Why are you sitting there? Why don't you go? You will be stretching your neck and... oh, you touched... So, cos alpha, but why is it even affecting? Okay. So cos alpha is ax over a, cos beta is ay over a, and cos gamma is az over a. I hope you can figure out these ratios from the figures. I think it's very clear, right? So from here now, you see we can go back here, because unit vector is ax over a, which is cos alpha, cos beta, and cos gamma, isn't it? So we can express the unit vector either in terms of the scalar components of the vector or in terms of the direction cosines or the direction angles. Okay? In which case it will become cos alpha a I plus cos beta j plus cos gamma k. Yeah. So this is another formula for the unit vector. However, when any two of the angles are known, you can find the third one, because they are related using this equation. Cos square alpha plus cos square beta plus cos square gamma equals 1. So if any two of the angles are given, you can find the third one, isn't it? Using this one. Okay? And then here also, we can find the Cartesian vector form using the unit vector, either using the coordinate direction angle or using the scalar components, isn't it? It depends on what is given from the problem, what is available, isn't it? Now, addition and subtraction of Cartesian vectors. Let's consider it's similar to the 2D problem, in which when you have A and B expressed in Cartesian vector forms, the resultant is A plus B. So we simply add them up together, but using similar terms. Okay, the coefficient of i's together, b's together, j's together, and k's together. Okay, using like terms. Same thing if r equal a minus b. Okay, we do the same thing. So the resultant force is just the sum of all the force components, isn't it? In vector form. Even if you have 2, 3, 4, 5, irrespective of the number, okay? And meaning you have to sum the components along the x-axis, isn't it? Along the y and along the z-axis. This we demonstrated for the 2D case, isn't it? So now, here, problem says determine the magnitude and the coordinate direction angles of the resultant force acting on the ring. You have a ring, you have two forces, isn't it? F1 and F2. Fortunately here, all the forces are given in vector form, isn't it? So we were just asked to find the magnitude and the coordinate direction angles of the resultant force, which is straightforward. We used our parallelogram to, depict the resultant. And then, in this case, no need to take the triangle and do all the calculation for the angle and what have you, because the vectors are already given in vector form. So all we need to do here is simply the resultant force is given by F1 plus F2. And then we add the component together, right? Very simple, straightforward, and direct, isn't it? And that's why all the problems we solved before, that is using the parallelogram law and triangle construction, we can go back and solve the same problem now using the Cartesian vector form, using the vector notation. But what are we going to do first? The first thing we do, we have to convert the magnitude of the forces to vector, to the vector form, isn't it? Using, depending on what is given, and you know, so we first convert them to vector form in this case, and then we sum them up together, and then we can find the magnitude and direction once the resultant is expressed in Cartesian vector form. So here we got the resultant force, and we can get the magnitude, isn't it? This way, and we can get to get the direction angles, okay? Because we are asked to get the coordinate direction angles. So to get the coordinate direction angles, we go back and use this formula for the unit vector. Okay? That cos alpha I, because now we have the vector, right? So we have this, and this is equal to that. So you can just compare the coefficients, because this expression is equal to this expression, isn't it? So it means cos alpha I is equal to this. Cos beta is equal, isn't it? So that's exactly what we did here. We expressed the unit vector, which is the vector of its magnitude. We know the magnitude, and this is the vector, right? So this over 191 over 192, you know, like that. And then it means the coefficient of I is cos alpha, the coefficient of j is cos beta, and that of k is cos gamma, isn't it? And then we can get alpha, beta, and gamma. Here beta is greater than 90, and since j component of the unit vector is negative, you know, you can see that it falls in the negative y-axis. Okay, so beta should be greater than 90, and sometimes you can use this to check whether your computation is right or wrong, because assuming you got beta less than 90, you know definitely your computation is wrong, because based on the figure, the resultant force should fall somewhere in the second quadrant, which will make beta greater than 90. Okay? Is that clear? Now we have another problem here which says you have two forces acting on the hook. Specify the coordinate direction angles of F2 so that the resultant force Fr acts along the positive y-axis and has a magnitude of 800. You have F1 300 Newton, F2 700. We are to specify the coordinate direction angle of F2, which is not given. For F1, it is already given, right? 45 is what? No, 45 is what for F1? In terms of alpha, beta, gamma. What is 45? What? Pardon? Alpha, yeah, alpha. Is the angle of inclination to the x-axis. And what is 60? Pardon? Beta. And what is 120? Gamma, isn't it? So F1 is completely specified. I mean, the coordinate direction angles for F1 is there. So we can find the Cartesian vector form of F1, isn't it? Using what? The unit vector, isn't it? So UF1 will now be given by cos alpha I, isn't it? Plus cos beta j, plus what? Cos gamma k. So we just substitute alpha, beta, and gamma, isn't it? And then we have the magnitude given, isn't it? Because this is equal to what? It's equal to F1 over its magnitude. Am I right? The magnitude is already given. So you can substitute alpha, beta, gamma, F1, the magnitude, and then get the Cartesian vector form of F1. Are you following? Oh. You came late. You came when I started explaining. Next time come, if you ask me to come again, I will not come again. You should be here before me, so that at least you don't take us back. Okay? We already explained the unit vector, which can be defined in so many ways. One is using the vector in Cartesian form over its magnitude. That is one formula for the unit vector. Another one which we derived, we realized that we can use the coordinate direction angles and define the same unit vector as cos alpha I plus cos beta j plus cos gamma k. So this is exactly what we are using. So this is equal to that. From this problem for F1, we have alpha, beta, and gamma. And we have the magnitude. So all we want to find is the vector in Cartesian vector form. So that's exactly what I'm explaining here. Okay? So for F2, the problem says we should find the coordinate direction angles of F2. Okay? And then we were given the resultant, and we were told that the resultant is directed along the positive y-axis, isn't it? And the magnitude of the resultant is 800. So can we form the Cartesian vector form of the resultant? Who can tell me the Cartesian vector form of the resultant force? It's directed along the positive y-axis, and the magnitude is 800 Newton. 800 G. Because it will have only one component. It will not have component along X and Z, isn't it? Is that clear? So it will just be 800 G, isn't it? Because it's directed along the y-axis. Okay? So now, you see, we have the Cartesian vector forms of F1 and the resultant force, isn't it? We want to find the direction angle of F2. That is what the question is saying we should find, isn't it? We can do that when we know the Cartesian vector form of F2, isn't it? Once we know that, then we can get the direction angles. So that's why we express F2 in terms of the unknowns. F2xi plus F2yj plus F2zk, which is what we don't know. We don't know the components, and we want to determine them. Are you following? We determine that of F1, isn't it? This, isn't it? We just substitute the angles and the coordinate, sorry, the magnitude, based on the formula I just erased, using the unit vector, isn't it? And then this is FR, so we just apply this formula, FR equal F1 plus F2, right? And then substitute. And then we can get F2x, F2y, and F2z, because they are the only unknowns, by comparing the coefficients on both sides, isn't it? So that's exactly what we did here. You see this 800 JFR, F1 plus F2, we sum them up. We sum the coefficients of I, J, and K. So the coefficient of I here is equal to the coefficient of I here, which is 0, right? That of J equals 800. That of K equals 0. And then we can find F2x, F2y, and F2z. Are you following? Yes. Now, having expressed this in the Cartesian vector form, the next thing is to find the direction angles, which this is F2, right? So F2 is given by F2 over its magnitude, and is equal to, isn't it, cos alpha I plus cos beta j plus cos gamma k. Now, we know the magnitude of F2, right? It's given from the problem, 700. We now know this one, isn't it? Is that clear? So, we can divide this by that, isn't it? And then get, because what it means is that cos alpha is just equal to F2x over the magnitude, isn't it? Which is exactly what you are having here. Cos alpha is just the component, the x component over the magnitude. Okay? The same thing for beta, the same thing for gamma. Are you following? Yes, sir. And then from there we can get our alpha, beta, and gamma, which is what the problem is saying we should find. So this is FR, okay? And when you complete the parallelogram, it gives the resultant. And then we have the coordinate direction angles for F2 now. Is that understood? Now, here it says you have the unit vector U of a force, vector F. O is what? What is the unit vector for this? We are basically going to review dot product, which is something you all
to find the unit vector
before.
is
You
vector
see,
of its magnitude.
the importance of this,
first find the magnitude,
you did
isn't
vectors,
it?
but then
and then divide.
There was some
Very
sort
simple,
of disconnect. You did vectors in mathematics.
Oh.
Then when you were doing it, probably
Any
you thought it has
questions
no
before we move on to
practical
the last
application.
one?
You are just learning
No
the
question?
mathematical
Clearly
formulas and
understood?
how to solve problems, and then
Because like I said, immediately after
try
this, we
to
will
get your
start,
A and forget about everything to do with vectors again, isn't it? Because then probably, you know, you are just treating them as vectors. You never thought these have real life application, because your quantities are either vectors or scalars. So those operations you learned are really actually going to be applied. So there was some sort of disconnect then. Not the same way that now, okay, you did linear algebra, you learned matrices. You thought it is just some academic exercise, you know, how to find determinant, how to find the inverse of matrix, this and that, as if you will never use it, I mean, in your different areas. But even now or here, we are going to use the concepts of matrices, because modeling is all about expressing our parameters as matrices and carrying out operations, vector operations here and there. And all those concepts, you will find them useful here and there. But then, when it was taught, you just find the determinant, find this, find that, and you thought, because sometimes you even ask yourself, why am I being overburdened? I mean, when I go to the office, because that time, that is what people usually say, that when I get employed and is working as an executive, who will ever bring calculus on my table, solve this dy by dx, isn't it? But as engineers, you should know better now. You know, all those mathematical rigors that you went through, they are all for a purpose. And they are all, you will find their applications in one area or the other. But then what happened was, when they were being taught, like the vectors, probably you never imagined it will have all these applications. Though we haven't even started the application yet, because it's after this that we will continue with our groundwater modeling proper, where everything will turn to vectors again. But all those mathematical background you had are really important. All the courses that you did, they are not just there to waste your time for nothing, but they are preparing you for the task ahead. So here we will just briefly review the dot product to determine the dot product of two vectors and to study applications of dot product. So definition of dot product: when you have any two vectors A and B separated by angle theta, A dot B, which is the dot product, is equal to AB cos theta. Although some may say, what? I know just multiplication. A times 2 times 3 is 6. So what is this dot and cross? They all have different meanings when it comes to vector operation. Okay? Here we will review dot product. I don't know, probably later, I don't know if there will be the need to review cross product as well, because we may have ourselves, we may find the cross product also important in some other respect. But for now, what is most important for us is the dot product. So A dot B is equal to AB cos theta. AB are the magnitudes of A and B respectively, and theta lies between the 0 and 180. So from this, what will you say about the result obtained from the dot product? Is it a scalar or a vector? Why is it a scalar? Because what? So A, B are all the magnitudes, and cos theta is another scalar, right? So scalar, scalar, scalar. So definitely the result is a scalar, isn't it? Yeah. It results into a scalar, not a vector. That is very important. Okay? And the laws of operation. A dot B equal B dot A. It is commutative, and multiplication by a scalar. A dot A into A dot B, you can multiply any of the vectors first, okay, and the result remains the same. And it is distributive. A dot, you know, just like opening bracket. As we are going to see, if you remember what you did on cross product is not commutative. A dot B is not B dot A cross B is not equal to B cross A, but it's equal to minus, because that one is direction. It has to do with the direction. It includes the direction, and it's because the result of a cross product is a vector. So meaning direction is important. So A cross B is minus B cross A. Now dot product of Cartesian vectors. When you have I dot I, what will be the result? The magnitude of I, isn't it? Times the magnitude of I times angle between I and I is what? What? Angle between I and I?
0.
And cos 0 is what? Why is it 1?
Cos 0 is 90. 1.
Cos 0 is 90?
No, I forgot.
So the magnitude of I is what? 1, because it's a unit vector. The magnitude of the unit vector is 1. Whether Cartesian unit vector or just ordinary unit vector, the magnitude is always 1. Okay? So 1 dot 1 dot 1, isn't it? So I dot I equals 1. What about J dot J? K dot K. And I dot J. Huh? Equals K? Why K?
Angle between them is 90.
And cos 90 is what?
0.
So J dot K,
0.
K dot I,
0.
0. You are being confused with the cross product. It is in the cross I cross J that is K in the cross product. So that's exactly what we did here. I dot I equal 1, okay? And then the cross terms are all equal to 0. Now, how do we take the dot product between two Cartesian vectors? If you have, yeah.
I wanted to say something about why cos 0 is equal to 1.
Yeah, I asked you, why is it equal to 1? No, I asked you, why is cos 0 equal, sorry, cos 0 equal 1, why?
Because when we press inside calculator, it give us 1.
No, the calculator has been programmed. It is someone that programmed it that way.
We were not taught. We don't know.
You are not taught, no. That I will not agree.
Have I lied, sir?
Yeah, so, is he lying? He's asking him. Answer him. Is he lying? And you have to answer him. Is he lying? You have to answer him. Is he lying? You have to answer. He asked you. Is he lying? You have to answer him. No. Is he lying? Huh? Okay, he's answering you. He's answering you. No, let him.
You were taught?
I came from a different school, so probably I was taught.
You came from where?
My student school is different from yours.
Okay. So
probably
Then tell us. Then he will tell us now. Because he said he was taught. Now tell us, why is it 0? So who can remember then? Because he claims that it's just program. You know, the calculator, just when you press cos 0, it gives you 1. But how that becomes 1, he said no, he was never taught. Someone said he was taught but has forgotten. So who can remember? From what? 4-figure table. Even the 4-figure table has a source. Even that one was written out like that. Yes?
I in some direction. So
So you cannot remember simple SS1 mathematics. SS1 mathematics. Then why is cos 90 equals 0? Even that one is programmed.
You know, the truth is, I was not taught. I just know when you have this, you
If I now show you how it becomes 0 or 90, you will remember that you were taught. I don't agree with you that you were not taught. You You must have done the sine cosine curves, isn't it? When you have theta here, isn't it? And this is cos theta. Cos theta. When you sketch the curve, the sinusoidal curve, can you remember this? Where this starts from 1, this is 0, and then it moves on like that. Sorry, no. This is 1, this is 90 degrees, and then it moves on. This is the cos theta curve. This is 0. That's why cos 0 is 1. Cos 90 is 0. For sine, it is like this. It comes the other way. Sine 0, 0. Okay, no. It should. Okay, yes, it's like this. Sine 90, 1. For tan, it is what? Can you remember this course? In SS1 mathematics? You have seen something like this? Okay.
Not well explained.
No. Whether well explained, even that one we can contest that one. Since you have seen something like this, it means you were taught this particular concept, but you forgot. If you say you forgot, but to say that you have never seen this before, no. I will not agree with you. Do you all remember this? That is how you obtain all the cos 0, cos 90, and what have you. And for 30 and special angles, 30, 60, 45, how do you got those ones? What is sin 30? No, it is a special angle. You are not expected to look at any table, any calculator. What is sin 30? What is sin 30? So how did he get that 0.5?
1/2.
How is that?
Also catch this triangle.
This is SS1 mathematics, special angle, sin 30, 45, 60, isn't it? Okay? When you see sin 30, cos 60, you're not supposed to get any calculator to point what is cos 60. It should be up here. Okay? That is, by the way, now we have A and B expressed in Cartesian vector forms, and we want to take the dot product between these vectors. We have dot, so we open the bracket, isn't it? AXI dot BXI, isn't it? So we have I dot I, because it is the vectors that, the dot product is being operated on the vectors, isn't it? For the scalars, we just take the ordinary multiplication, okay? So we have I dot J, and then I dot I is 1, I dot J 0, so all the cross terms cancel, and this is 1, this is 1, and this is 1, okay? So what we are saying here, when taking the dot product, is just the same thing as saying we multiply the corresponding coefficients of i's together, j's together, and k's together, okay? If you look at the end result, ax times bx plus ay times by plus az times bz. Now the application, of course, in determining the angle between two vectors, okay? When you have two vectors given in Cartesian vector form, you can always find theta if the two vectors are given, or if you can find a way of getting the Cartesian vector forms, isn't it? So theta will be cos inverse of A dot B over the product of their magnitudes. Then another application is in determination of the components of a vector parallel and perpendicular to a line. Here you have a line, A prime line. It can be any axis, but here it is being generalized, okay? You have a vector A. When you resolve it horizontally, you have A cos theta as the what? Scalar, isn't it? But if you want it in vector, previously we used I, isn't it? But here we are just using any line. So we use U, which is the unit vector representing that axis. If A prime is x-axis, it becomes I, isn't it? If it were to be y-axis, it becomes J, isn't it? But in general, it is A cos theta U, where U is the unit vector of that axis, isn't it? And to get the perpendicular component, we can use, because A is equal to A parallel plus A perpendicular, isn't it? Using the vector notation. Or we can use Pythagoras if we want to use the scalar notation. But if you look at this one, the component, which is A cos theta, this is the magnitude of A times cos theta, isn't it? It's the same thing as taking the dot product between A and unit vector in the direction of A, isn't it? Because the unit vector magnitude is 1. The magnitude of A is this one, isn't it? So it's just like you have A and the unit vector, isn't it? And the angle between them is theta. So A dot UA is this cos theta, isn't it? From the dot definition of dot product. Are you following? A dot B is equal to AB cos theta. But the magnitude of UA is what? 1. So that's why it disappears here. Are you following? And this gives the horizontal component, which is AX. Because this is the horizontal component of A, isn't it? Along the A axis. What am I saying? This is the horizontal component. The scalar component along this axis is A cos theta, isn't it? Which is equal to A dot UA. Okay? And to get the vector form, we just multiply by the unit vector. Just like we have Fxi, Fyj. Very simple. Because Fx is what? F cos theta. Isn't it? And Fy is what? F sin theta. Right? And like I said, to get the scalar component of the vertical, we can use Pythagoras. Or if we have them in vector form, we can simply subtract A minus A parallel. We'll take some simple examples here and then say goodbye to the vector revision. But then now, I need to introduce something called position vector. Position vector. Okay? What is a position vector? Position vector, you see, in the 3D case, we only want to know how do we move from the origin to a particular point in space. When I say in space, I mean in 3D, isn't it? So how do we move from the origin to that point? So we'll be using the coordinates. How much do I move along the x-axis, along the y-axis, along, like if I want to get to point B. First of all, what is the coordinate of B? From the origin, I move 2 meters, isn't it? On the x-axis, 6 meters on the y-axis, and 3 meters on the z-axis. Am I right? So the coordinate of B will be 2, 6, 3. Am I right? Because coordinates are expressed in terms of x, y, z. X, y, then z. Are you following? So that is the position vector. But then, no, this is y, x, z. Like I mentioned, if you have any point here, let's say point A, this is the origin, right? And position vector is designated using R, small letter R, and it has to have a subscript, just like the unit vector. Unit vector must always be written with a subscript to indicate the force that it is, giving direction to. The position vector must indicate the points it is connecting, 2 points all the time, isn't it? Because it is, how do I move from this point A to point B? Okay, so it must have a subscript. So if this is point A, so this is the origin O, so it will be what? OA. So position vector between OA. So how do I move from point O to point A? Are you following? But then this is the origin. Usually when the first point is the origin, we don't indicate it. Okay, so instead of writing ROA, we can just write RA. When you just see one letter, it means it is the position vector from the origin to that point. So RA means from the origin O to point A. Okay, so if the coordinates of A is given as x1, y1, z1, isn't it? So how do I move from this to this point? Okay, that is the position vector. And since it is a vector, so it will be given by the difference between the coordinates. I move from O to A. So the coordinates at A minus the coordinates at O. Okay, so it's going to be x1 minus 0. So it's going to be x1i, isn't it? Because it's a vector. Okay, plus y1j plus z1k.
The y will be in the other direction. That's minus 1.
What?
Y will be.
No, this is the coordinate. Don't worry. This is the coordinate. The actual value will dictate whether it is. This is generalized form. Okay. Don't worry. When we begin to take numbers, you will see whether it's positive or negative. Now, from here, if you have another point here, B, let's say B, okay, whose coordinates are x2, y2, and z2, okay? How do we define RB now, isn't it? So RB will be defined in the same way, right? It will be x2i plus, okay? Now, how do I move from A to B? This is RA. This is RAB, right? Because now it's starting from A and ending at B. This is RA because it starts from the origin. Instead of writing OA, we'll just write RA. The same thing here. Now, how do I move from A to B? From A to B, I now subtract the coordinates. the position vector at B minus the position vector at A, isn't it? The coordinates of point B minus that of point A, isn't it? Which is now going to be x2 minus x1i, isn't it? Plus y2 minus y1j plus z2 minus z1k, right? Okay. Now, another question. From this figure, which one is the resultant position vector? You remember when explaining the resultant, using triangle construction, we gave some formula, some tips on how to identify the resultant vector from the triangle, isn't it? Yes. So from this triangle, who can now tell me the resultant position vector based on that rule? What? RAB? RB? What other option do we have? RAB? Who agrees with him? RAB. RAB. Why? Why is it RAB?
The resultant between RA and RB.
And what is that formula that we used? What is the rule that we used in identifying the resultant? So did you use that rule here in saying that RAB is the resultant position vector? Okay, let's apply the rule. You say head to head, right? Oh, so this is head to head. So what about tail to tail? Is this tail to tail? This is tail to head. It didn't pass. What about this one? This is tail to tail, head to head. So RB. If you remember, I told you that, I asked you, is it always the case that the longest side of the triangle is the resultant? I think that is what is confusing you here. You thought the longest side will always be the resultant, and I told you no. That is not a rule. When you have a triangle whose sides are all vectors, the only golden rule to be used is HHTT, head to head, tail to tail. Simple. So you look at the configuration and see where those rules are satisfied. And that side is now the resultant vector. Is that clear? All right. So resultant position vector is a vector. So we can redefine the unit vector in terms of the position vector, which is now the position vector over its magnitude, right? The same thing as we did for the vector, which is, let's say, A over its magnitude. Because this is a vector, that is also a vector. Okay? So now, let's move on to our example. Oh. What is it now? Start it afresh. So okay, but you see, one of the importance of using the position vector is that we can use the position vector to get the Cartesian vector form of any vector, because the position vector can be defined in terms of the unit vector can be defined in terms of the position vector or in terms of the vector itself, isn't it? So it means if we have vector A and we want to determine its Cartesian vector form, we can do that if we can determine its position vector. Am I right? If we can determine its position vector, we can now use this equals that, and then we can get this one, isn't it? This is now the third way, the third way of getting the Cartesian vector form of any vector using the position vector. Okay, and that's exactly what we are going to use here. And we know for position vector we use coordinates. So the first thing we do is to determine the coordinates of point in space, isn't it? So here it says we have a frame in this figure that is subjected to a horizontal force F equals 300J. Can you see? It's definitely 300J because it's directed along the y-axis. And determine the magnitude of the components of this force parallel and perpendicular to member AB. Parallel to member AB will be this, and perpendicular will be that, isn't it? So the first thing we do here is to try to get the force vector, isn't it? For AB, we just assign a unit vector UB, which indicates the direction of B. So here, if I like, I can say UB, which will be the position vector of B over its magnitude, isn't it? But the first thing we do is to determine what is this one. What is the coordinate of point B? I think I just did it, right? What is the coordinate of point B?
2, 6, 6.
So you just look at the figure because it is 3D. Once the geometry, once the geometry is given, so you can open your eyes and look at exactly how do I move to point B from the origin, isn't it? And you usually start from X, Y, Z, keeping in mind the positive directions of X, Y, Z and the negative directions of X, Y, Z. Because if you move downward, that's negative Z, isn't it? So the coordinate of B is 2, 6, 3, right? So what is the position vector RB? It's going to be 2i plus 6j plus 3k. And we can get the magnitude. And then the unit vector is given by this. Simple, right? And then from there, we can move on. to get the first vector, because we want to get the magnitude of the component of AB. And to get that, FAB is going to be F cos theta, or F dot UB, which we did before. How we got 2, 3, 6? Do you understand this 3D figure here? X, Y, Z. Can you see the dimensions? How do I move from A to B? From the origin to point B? On the X, Y, Z. I first move 2 meters here, isn't it? No, it's measured. Look at it very well, it's measured. Measure what? No, look at the figure. The figure is given. Yeah, it's given from the question. This is given from the question. This is our construction. This is given from the question. Is that clear? Showing the dimensions. Okay? So, how much do I move? How many meters do I move from O on the x-axis? 2 meters, right? And then 6 meters here, and then 3 meters up. Then I will be at point B. That is the position vector. Is that clear? So the position vector for B is 2, 6, 3. So in vector form, 2i plus 6j plus 3k. Are you following? Now, if you remember in this, we said the component is going to be given by A dot UA, isn't it? So that's why in this we got the position vector. So we take the dot product between the position vector and the vector. The dot product between F and UB, which is exactly what we are doing here, because the component of FAB is going to be F dot UB. F is given as 300J, UB we found it, isn't it? So we now take the dot product, which is what we did here to obtain the magnitude of the component parallel to AB. Are you following? Now, yes. Pardon? Oh, okay. You are answering. Oh, so that is AB. To get the vector form, to get it in vector form, we got the magnitude. So to get the vector form, we multiply by the unit vector, isn't it? Which we already obtained here, isn't it? So we multiply the magnitude by the unit vector. This is supposed to be written in bold. It's a mistake, okay? It is supposed to be in bold because it is a vector, okay? So we now got the vector form, and to get the perpendicular one, this is in vector form, this is in vector form. So how do you express F in terms of FAB and F perpendicular?
F is equal to FAB plus F perpendicular.
Yes, because usually when you have the parallelogram, you can look at a side and know whether it is the resultant or not. If you can see the diagonal, then the diagonal is always the resultant vector. But for a triangle, you cannot look at a triangle and determine if I were to form a parallelogram, which side will form the diagonal. You may have several parallelograms from one triangle. So that is why that rule, tail to tail, head to head, that is where it comes into play. But for a parallelogram, if you have a parallelogram and the diagonal is spelled out, the diagonal is always the resultant vector. Is that clear? So that's why F is just given by FAB plus F perpendicular. F has been expressed in Cartesian vector form, so also FAB. So we just subtract. Simple, isn't it? And straightforward. We just subtract. Or if we want to use the scalar form because we want to get the magnitudes, we all have their magnitudes. FAB, this is the magnitude. F, we know the magnitude is going to be 300 because it's just 300i. So the magnitude without even using any formula, square root of 300 squared, which will still cancel out to give us 300. Isn't it? So the magnitude is just 300. So either way, we get the perpendicular component. Is that clear? We'll take some break, okay? Then when we come back, I hope we got refreshed this example. So, and then probably conclude this particular revision. Okay?
On to the last example.
Let's take about 10 minutes break.
Here we have a pipe
What?
that is subjected to the force F
Okay.
equal 80 pounds. You can see that at point B. Determine the angle theta between F and the pipe segment BA and the projection of F along this segment. We want to find the angle theta between the force and BA and the projection of F along BA. Very simple, straightforward, but probably not very direct, because here the force has not been given in Cartesian vector form, isn't it? So we need to get the Cartesian vector form of the force. But before then, the vector product of two vectors A dot B is given by their magnitudes times cos of the angle between them, right?
These vectors can be forces. They can be position vectors as well. In this case, we have only one force. So, but from the geometry of the problem, we can get the position vector BC and BA. Am I right? So, we cannot just use, we have only one force, but we can get position vector BC and BA, and then we can find the angle between them using this one. Are you following? So the first thing we should do is to get the position vector BA and BC, and then get the angle between them. Is that clear? And that we can do by determining the coordinates of point A, B, and C, isn't it? Right? Let's start with point B. What is the coordinate of point B? Yes, let me ask this gentleman. What's your name? Muntaka. So, what is the coordinate of point B? Position. Yeah, the coordinates. You know, you did coordinate geometry, right? Math 104, isn't it? So, coordinates and coordinate geometry. You start with coordinates, right? Coordinates of points. So, what's the coordinate? What are the coordinates of point B? By coordinates here, it means from the origin. How do I move to point B? Isn't it? Just the same way I demonstrated the use of the position vector. The x component, the y component, and the z component. Yes. It's not very clear. Are you sure? Yeah. Look at it very well. Are you sure it's not very clear? Is he saying that, I mean, do you agree with him that the origin is not clear from the figure? Who agrees with him that the origin is not clear from the figure? It's clear? Oh, someone says it's clear. Look at y, look at x, look at z. Where they met is the origin, this point. Simple. Am I right?
Yes.
So how do I move from the origin to point B? How many feet do I move on the x-axis, on the y-axis, on the z-axis? That's all I'm asking. Okay, now tell me.
3 feet, 2 feet, 3 by 3.
3, then what?
3, 3, and then
what? 3, 3, then 2? Okay, he says 3, the coordinates of B is 3, 3, then 2. Is he right? I don't know. Let's have a judge here. Is that coordinate correct?
no.
It's not correct?
Yes.
Is it correct? You don't think so? Then what do you think? 2, 2, 1? 2, 2, 1. Oh, no?
2, 3, 1.
2, 3, 1. Correct?
No.
No.
So with the same convention over
3, 2, 2.
with the same convention over.
Is it correct? I only want the coordinate.
Okay, so second to last. Even without sign convention.
It's 2, 3. 2, 3, 1.
Okay, let's examine each one. Don't worry. We have 4 entries here. Let's examine. Let's examine them. This is the origin. This is point B. To come to point B, I have 2 routes. But I want to start with the x-axis because so as not to get confused, because in the coordinate, we always start with the x-axis. So I prefer, but you can have 2 routes. You can always sometimes start with a y or x, depending on the point, or where the point lies, isn't it? Here I want to move from, I want to start with the x-axis. From here I move to this point, 2 feet. Then I come 1 plus 2, 3 feet. And then I go down, minus 1. So 2, 3, minus 1. Let's see which one. 2, 3, minus 1. Oh, this is 0, 0, 0. Then here I put minus 1 and then tick this one. Because it is down, isn't it? Towards the negative z axis. Are you following? So this is the coordinate of B. What?
I don't follow you. Sorry, please. Can you just repeat yourself? How you get that 3? That's what I want to get.
3. On the y-axis, here I move from the origin to C, right? And then from here I come to this point, which is giving 1 plus 2. That's why for 3D problems, you have to open your eyes very well. You just have to open your eyes very well. If you're feeling sleepy, better go and, wash your face so that you can see clearly. Yes. No. Wherever you start, you arrive at the same value. Okay, let's take the second route. From the origin, I move 3 feet on the y-axis, isn't it? Then from here, I move 2 feet on the x-axis. And then 1 feet down. So it's 2, 3, minus 1. So whichever route you decide to take, either from the x-axis or the y-axis, you'll arrive at the same. But why I'm starting from the x-axis, so that you don't get confused and place 3 in the position of the x-coordinate. Did you get my point? So that is B. What is the coordinate of point C? Now you tell me. Yes.
Point C?
Yes, point C.
How do you get to point C?
Yeah, just tell me the coordinate x, y, z.
Okay. We have 2. Then we have 3. Then we have coming 2 to the x, 3 to the y, then z.
Mm-hmm.
0.
So what are the coordinates?
I just said 2, 3, 0.
2, 3, 0.
Yes.
Where did you get 3? This is the origin. You just move 2 units, 2 feet on the x-axis. You don't move along the x, along y, along z. It is along x, so the coordinates on y and z are all 0. Isn't it? Okay, if you got that one, now tell me A. If you don't get this one, then it means what's the coordinate of point A? Yes.
It's just 1.
What do you mean by 1?
As in 1 to the y direction.
So give me in terms of x, y, z.
Okay, we have 0, 1, 0.
Okay, so now I know that you understood. So 0, 1, 0. So from the coordinates now, we can get RBC, isn't it? And RBC will be the coordinate, RBC will be the coordinates at C minus the coordinate at B, isn't it? This is for C, for A, and for B. So the coordinate at C, 2 minus 2, 0. 0 minus 3, isn't it? So minus 3i, and 0 minus 1, 1k, isn't it? That's why you have it, minus 3j plus 1k. The same thing for BA, you subtract. Okay, this is A, this is B. So it's going to be BA, so A minus B. 0 minus 3, minus 3i. 1 minus 3, minus 2j. 0 minus 2, minus 2k.
No.
Your pointer.
Oh, I'm using this one, the wrong one, sorry. Okay, so this is the correct one. Is that clear? And we can get the magnitudes, and then we can get the angle between them, because we take now the dot product, isn't it? By multiplying the components of i's together, the coefficients of i's together, j's together, and k's together, and summing them up. Are you following? Now, having obtained the angle, but then again, we can get this position vector without having to necessarily write down the coordinates and then subtract. We can look at the figure as it is and come up with this expression, straightforward. Is that clear? This is the longer route, but this one you need to open your eyes, because what is BA? BA, it means how do I move from point B to A? How many units do I need to travel on the x-axis, y-axis, z-axis? Simple. From point B to A. So let's start. From point B, I first move up, isn't it? Which is plus 1k, isn't it? So the z-axis is 1. And then I move 2 units on the x-axis, negative x-axis, because I will move this way, which is minus 2i. And then I move 2 units on the negative y-axis, which is minus 2j. So what do I have? Minus 2i minus 2j plus 1k. Isn't it? By just looking at the figure, without going through generating the coordinates and then subtracting. Because in some problems you may need to generate a lot of position vectors. So going through the longer route will really take a lot of your time, and precious time for that matter. Okay? So the other one, BC. How do I move from point B to C? I just move up and then this way. I move up 1k, then 3 units on the negative y-axis. So minus 3j plus 1k. Isn't it? Because this point and this point are having the same coordinate along the x-axis. This is 2, this is 2. So that's why there is no component along the x-axis. Are you following? So you see, this is like a simpler method, but you need to be very careful, isn't it? With the sign conventions, moving up along the positive direction of the axis or negative direction of the angle. Sorry, of the axis. And then having obtained the angle, the next part of the question says we are to determine the projection, determine the angle between this, and the projection of F along this segment. The projection of F along BA. So to find the projection, the first thing we shall do now is to find the Cartesian vector form of the force. Because the force has been given in magnitude only, isn't it? So we need to express it using the Cartesian vector notation. And how do we do that? We can, of course, use the position vector, isn't it? Because the unit vector, BC, isn't it? In the direction of the force, isn't it? Is equal to the force vector over its magnitude, right? And is equal to the position vector, BC, which we found, isn't it? Over its magnitude. Can you see that? So now we can use, this is given, this is known, and this is known, so we can find this one. Simple, am I right? So that's exactly what we did here. You see, AT is the magnitude, then times the position vector, or the unit vector along BC. This is that, and the magnitude is this. So we can get the first vector. And once we get the first vector, the next thing, to find the component along BA, the scalar component. This is the scalar component. Okay? We just take the dot product, isn't it? Between F and UBA. But we don't have UBA. This is, we already have it, UBA, isn't it? Found here. Because from BA, we can divide by its magnitude, isn't it? So we have this, we have that. So we take the dot product. And that is it. Alternatively, because it's just like resolving the force along this, we have the angle found, isn't it? So you can simply say it is F cos theta, which is exactly what we did here, F cos theta, and you will arrive at the same answer. Is that clear? Understood? Okay. So let's see this one. It says we are to find the angle between these two forces. And how do we find the angle between the two forces? We find the magnitudes and then take the dot product and then apply the formula, isn't it? Because the forces are all given in Cartesian vector form. If they are not given in Cartesian vector form, the first thing we need to do is to express them using the Cartesian vector notation, isn't it? But here the job has been simplified. And then this one is saying the magnitude of the component of the force F along a line AB having position vector is given by what? You have a force, you have a line AB. The position vector of the line has been given. So what is the magnitude of the component of this force along this line? From the position vector we can get the unit vector of the line, isn't it? From the unit vector we can take the dot product, which will give us the magnitude of the force along that line, isn't it? Very simple. And the force was given in Cartesian vector form. And then, yes, we are done with the review. Then in our next class, we'll continue. We'll continue with the aquifer properties. You remember we just digressed. We are discussing about the aquifer properties where we classified the properties into three. We have the storage properties, which we considered porosity, yield, specific yield, and specific retention, and storage coefficient, storativity, isn't it? And specific storage. This we explained, isn't it? And then we are to move to the next, which is the transmission properties, which where we are going to consider two things, the hydraulic conductivity and transmissivity. Okay? And before then, that was when I stopped over to digress a bit. Because now we'll move to the transmission properties to start looking at the hydraulic conductivity, or basically the Darcy's law. Okay? Where you will see a lot of the application of the vector algebra that we did just now. Okay? So, in our next class tomorrow, we will continue. But make sure you review all the vector algebra very well, because it will show in the next class. Okay? Because now there will be no excuse that, oh, I forgot. Oh, I was not taught. Oh, I have never seen this before. That will not happen, because I know that I taught you this myself. So there will be no excuses. Okay? Make sure you go over all that we did before the next class. So any question? No question. See you tomorrow.